right, with this, we're all set. So let's begin. Thank you very much for joining us today, Kevin Uning, and also other members from the group. So the Open Raman project has been a really interesting resource online. We've already seen the page and been inspired by it for the last couple of years. And I think there's some YouTube videos as well, if I'm not mistaken, that we've watched a while ago. And yeah, you have a publication out as well, and there's a lot of interesting development going on your site. And we're really interested to hear more about the project from you, and then afterwards we have some time for discussion.
Great. Thank you very much for the kind introduction, and thank you, LIBRE Hub, for providing this opportunity to us to share a little bit of our work. So this work has actually been a huge collaboration between 4 different groups along from our side, the UCL, from the King's College, South Denmark University, as well as the Boston University, of different groups. We come from different backgrounds, and we realize that there is currently a need for this kind of like modular open Raman microscopes. And so this led to this project, which is titled the Open Raman Microscopy, a modular Raman microscope setup with an open source controller. Okay, but I think I'm getting a little bit too excited and ahead of myself. And so I would like to start a little bit maybe with the background on the fundamental mechanism behind ORM, behind Raman microscopy, which is Raman spectroscopy. As some of you, I think most of you would know, Raman spectroscopy is a very powerful analytical tool. And it is so because it allows us to probe into a molecule's vibrational energy level. By doing so, we are able to get the measurement that are representative of each molecule's own fingerprint. And this would then allow us to trace back the presence of such molecules, of these molecules in our samples. And it does so while being label-free and non-destructive to some degree. This is what makes Raman spectroscopy quite interesting into like several different applications. But what's more interesting than a single Raman measurement is actually multiple, or a mapping of Raman measurements, which is also known as Raman microscopy. By performing a mapping measurement of our sample using Raman spectroscopy, people are able to obtain a hyperspectral imaging of your sample. Here in the middle, we are seeing an example of such measurement, where each and every single pixel is actually a Raman measurement. A Raman measurement. And by looking at different wavelengths over here, we can then plot a heat map of it. And what's interesting over here is that by looking at different wavelengths, theoretically, we would be able to look for the presence of different materials. And what this allows us to do is to perform kind of like a layer analysis, for example, in tissue analysis or other applications. This can be done in both 2D and 3D imaging. And so these are really what people are interested in when they are talking about Raman microscopy. Now, if someone is interested in performing their own Raman microscopy, there are currently 2 main ways in which one can do so. The first one is to build your own Raman microscope. And as most of you can probably imagine, this is not so straightforward. There is a huge technical barrier in terms of like skills and experiences that you would need in optics, design, as well as programming. And so the other method that currently exists is to buy one. Here is an example of such system. There are currently several different manufacturers, notably Rationale, Whitech, as well as Thermo Fisher, that provides different solutions for these needs. And here is an example of a Rationale Invia confocal Raman microscope. It is a very nice system in which it has a built-in Raman spectral library, automated measurements. It is also capable of, it also has like built-in analysis techniques, which makes it appealing into a certain group of industrial or, well, commercial applications. However, these systems tend to also be a little bit limited in hardware configuration, has some degree of proprietariness in their software, and can also be very expensive. For some of us, some of the other users out there, potential users, if you would, especially us, academics, we tend to need something that's a little bit more flexible and modular. And this is because depending on the applications that we have, then the kind of Raman microscope that one would need might differ. For example, if someone's interested in doing a cell imaging, specific cell imaging, for example, one might this specific application might require laser excitation of 532 nanometer, a certain degree of confocality, and some mapping resolution of, let's say, less than 1 micrometer. However, if in the future the same group decides to perform tissue imaging in addition to their pre-existing cell imaging project, they might require completely different requirements, completely different setup with a 785 nanometer non-confocal for high throughput measurements and a different mapping resolutions. And what this means is that depending on the application, then the required laser source, the required spectrometer, stage choices, for example, will differ. And so there is currently a need for a modular system so that bespoke and evolving requirements can be accommodated. So seeing this need, we took it upon ourselves to design our own system, which is called the Open Raman Microscopy. To start with, we started with listing down the requirements that we are hoping to address. Here, these are condensed into 5 main requirements. The first one is that it has to be modular in terms of both hardware and software, naturally. Second of all, it has to have a range of cost to fulfill different kind of price points. Third, it has to have a fast mapping. Fourth, so that it's actually usable. Fourth, it has to be easily adaptable into any lab space and any data processing or data acquisition pipeline. And finally, it has to be developable into the future in terms of hardware and software as well. Okay, so based on these requirements, we then arrive at this. We then decided to use this what do you call this setup over here, this design over here, which is not our invention. This has been around for a long time ago. In fact, it's been confocal Raman microscopes. Confocal microscopy has been around since 1990s, I believe. But just to talk you a little bit through it, it is started with a laser source, which is then inserted into our system through a beam expander, through the bandpass filter, and then into the objective and condensed down into the sample. This then excites the Raman scattering, which are collected by the objective through the dichroic mirror, through the long pass filter, and then condensed down into the confocal fiber. Here, the interesting thing is that the confocal fiber itself acts as the pinhole to allow the confocality of our measurements. And this can be easily swapped out with a bundle fiber. And what this allows us to do is that because we are using a bundle fiber, it is able to receive a lot more signal simultaneously. And so this would then allow a more high throughput measurements. As briefly mentioned a little bit, different applications would require different specifications and different configurations of our system. And so we have tried to test our system based on 3 different configurations, based on 3 different applications. Here on the left, we have a confocal setup where it uses a single fiber for organoid scannings. And then in the middle over here, we have a high throughput bundle fiber using the bundle fiber configuration that is here in the LCN at UCL, where it is typically mainly used for surface enhanced Raman spectroscopy substrate mappings. And so it does not require any confocality. And similarly, here we have a completely stripped out system where it doesn't have any optical imaging system, just using a webcam over here and a Raman probe that is attached to a Z stage and automatic X-ray stage for the mapping of larger objects. Here, we would like to highlight that all of these three configurations are supported by our softwares, and it can be very easily adjusted or swapped out to accommodate one or another. So, moving back to like the big to the main classes of these 2 more modular ones. To allow this modularity, we have decided to build everything on top of the Thorlabs Cerna module platform. And what this allows us to do is that it allows us to use standard optomechanics components that you would typically use in an optical table. Instead, here we are building it on top of our microscope itself. The spectrometers, XYZ stages, and microscope imaging components are modular, and they can be easily exchanged within one another. And to support this hardware modularity, we also have developed the different controllers for each of them. Here we currently support a variety of devices. For the spectrometer, we support the Princeton Instruments Pyxis family, the Ocean Optics QE Pro family, and it is still in development, but we will be supporting the Endor spectrometers as well. As for the XYZ stages, we have the 4-Labs Kinesis family, physics instrument XY stages, as well as the Zabers stages. And for the microscope imaging, we support any kind of 4-Labs scientific cameras, as well as webcams. Okay, so equally important to the modularity of the hardware is the operation of the hardware as well. And I feel like this is one of the more challenging things in building one's own Raman microscope, because it is apparently not so trivial. So here we have developed our own software, and here is a little bit of a demo video of what it is and how it is like to use. So just to give you a little bit of introduction of the software, it is capable of doing naturally some basic controls of like moving the stages around, setting the integration time of the spectrometer, and among other things. On top of this, the program is also capable of automatically generating the coordinates required for this mapping, and that was what you were seeing before when the user was clicking the image of this B11 mark over here. Based on these coordinates, the users can then perform automatic mapping as well as automatic image styling. This is where the user would be able to combine and stitch different images obtained at different coordinates. Oh yeah, and finally, it also has some form of basic data management system at the back. Okay, so moving back to the list of requirements for the ORM, one of the main requirement and one of the biggest requirement here is actually fast mapping. And turns out it is not so easy to develop a fast mapping software. Software. The hardware themselves supports different kind of rates and different kind of like controls. However, it has to be accommodated along with the software itself. Here we have taken inspiration from the commercial softwares out there, and we decided to implement two main mapping methods: discrete mapping method and continuous mapping method. As the name suggests, discrete mapping method stops for each measurement. That is to say that the stage would then move to a certain coordinate, performs the Raman measurement, wait for it to finish before moving on to the next one, and repeat, and so on. Whereas in the continuous mode, when the stage would move in a snake pattern or a raster scan, and while it is moving, the spectrometer would then obtain would then perform Raman measurement continuously, one after another. Yes, and what this means is that we were able to reduce down the mapping time down from 52 minutes in this very specific case of this B11 mapping down to just 3 minutes over here. And this would depend on the amount of resolution and the scan area, but it is quite a significant improvement. Now, there are different pros and cons for the use of discrete versus the use of continuous method, but this will be left up to the users depending on the application that they are interested in. For example, discrete mode might benefit applications that require some photo bleaching controls, whereas continuous modes might benefit those with high throughput measurements. Okay, so. So another key feature that is required in most, I would say all Raman microscope is calibration, and we have taken this seriously in the sense that ORM supports two main calibration for the spectrometer calibration as well as the objective calibration. The spectrometer calibration is implemented to ensure that the wavelength that is reported, as well as the intensity that is reported from the spectrometer, is repeatable between different measurements of different groups and of different days. These are currently what you're seeing is the peaks from polystyrene, and ideally one can also use a specific calibrant that is agreed upon by the fields. The second thing is the objective calibration, and this is done to calibrate the scales of your image. This would then allow us to have a lot more higher level features, such as feature tracking, as what you're seeing at the moment, as well as image styling and the heat map overlay and among other methods. Okay, so now that we have the acquisition part, equally important to us is to be able to extract the data as well. And here, unfortunately, the Raman microscopy field doesn't yet have a field standard format. And so here we decided to make our own format to optimize the speed and the efficiency of our saving system. However, we realized that in the future there might be some changes in terms of the format standardization, and so we made it in such a way that this can be easily adapted into any kind of data analysis pipeline and any kind of formats into the future. Here at the bottom, you are seeing an example code that would extract the data, and this can be done in just in just 3 lines of Python codes. And so hopefully this would allow users to be able to adapt and integrate ORM into their pre-existing lab space and data analysis pipeline. So speaking of development, one important thing is to be able to develop ORM further into the future. And we started with a very simple structure, actually, and we thought that it would be a simple thing and an obvious thing to develop into the future. However, with more and more features that are being implemented, it turns out to be the final software architecture turns out to be pretty complicated to support fast mapping and the other modularities. So here, what we decided to do is to separate some specific layers so that the rest of the layers are locked to be developed by high-end developers, whereas the other ones, the green ones over here, can be developed or can be easily exchanged by normal users. This is especially important for the camera controllers, stage, and spectrometer controllers, which would allow the modularity of the hardware itself, as well as extensions in case that some specific applications require some very specific macros, for example, or the use of a specific pathway generated for the mapping itself. To support this developability into the future, we have decided to code everything down in Python, as well as provide what we hope to be a sufficient technical documentation for future developments. All of these things, including basically the entire thing, will be made available through GitHub and will be open source as we publish it. Okay, so finally, I would like to just show you a little bit of the ORM demonstration of imaging at varying different scales. Here we have the imaging of a microchip, a lens, tissue fibers, and cartilage edge, and showing you the Raman mapping. Here we have technically this is fluorescent for the left side and this one, but we can see that it is able to accurately represent and replicate the features that we see over here. And in case that any of you are wondering what the 4 was about at the start of the presentation, this is actually coming from a 384 well plate, and what you're seeing is the polystyrene peak of it over there. This ORM, specifically our one, is designed so that it is capable of performing high throughput measurements, and this is intended to support, again, a wide variety of different applications, including like high throughput measurements of 384 well plates that is able to cover the entire plate. Actually, it is not being shown over here, as well as 96 well plate and other formats as well. So in conclusion, there is currently a need for a modular Raman microscope for bespoke and evolving requirements. Here, with the Open Raman Microscopy, we hope to address this need with its modular hardware and software, intuitive graphical user interface, hopefully, automatic mapping capability, low and medium cost, fast mapping, universal data output format, developability, and simple adoption. Finally, it will also be open source in the in the very near future. We would like to thank all of these organizations as well as all of these groups and people without whom we wouldn't be able to develop this system. And thank you for your attention. We would like to welcome any kind of inputs and contributions to further advance the ORM. Thank you.